We already studied about the concept of pipelining in computer architecture, how various how a pipe is created, and there are segments that in each segment there is some processing going on, and no segment remains idle. And because of this pipeline structure, we increase the performance of a computer. More operations are uh, executed, are performed per second because of pipelining. And we can implement pipelining at arithmetic level as well as at instruction level. So if we implement it at arithmetic level, we create a pipeline for doing arithmetic operations, then that is called an arithmetic pipeline. It is usually found in high-speed computers, this type of pipeline, and especially in those computers which are mainly related to doing arithmetic operations, like be it floating point operations or fixed point operations, and similar scientific calculations, where a huge number of calculations are to be repeatedly done. It is a very successful way of doing those operations quickly, this arithmetic pipeline. Let us take an example of a floating point addition and subtraction and see how a pipeline structure will be for this thing. So floating point addition and subtraction are arithmetic operations, addition and subtraction, and we are operating on floating point numbers. In this, to create such a pipeline, it would be of this structure, and there will be 4 segments in this pipeline, in this pipe. And what will be the job of those four segments? It is mentioned here. We will see them one by one. And let us first see a problem here to understand how this pipeline will work. For example, we have two numbers, x and y. Fine, both are floating point numbers. First thing we need to do is that we need to normalize them. So if you see here, this is 0 point this thing. Fine, after dot there is no 0, and things are in this format, 0 point. So this is normalization. So here normalization has been done on this number. You can see this number is something like 950.4, and it is normalized and kept like this. In the same way, we have another number. It has also been normalized. Fine. So on this we have to perform operation, either addition or subtraction. But we should remember that whenever we input something to a hardware, it will be in binary. For simplification purposes, we are writing here in terms of decimal, but actually it will be in binary here. Right? Now, after normalization, we have x this and y is this. These are floating point numbers, and this thing we will call as mantissa, fine, and this we call as exponent. Right? 3 for here, the exponent is 3, here it is 2. So these are mantissas and these are exponents. So now we can say that we have two categories. One is category of mantissas, another is exponents. If I have to perform an addition or subtraction on these two, it obviously cannot be done directly. We have to get the exponents in the same form. So if it is 3, it should be also 3. If it is 2, this is also 2, then only we can do an addition or a subtraction. So the first thing we should do is that we should subtract the two exponents. So exponent of this x and the exponent of y should be subtracted. Once we subtract these two, it becomes 3 minus 2, that is 1. Fine. this one implies that uh, the exponents are different, and since this is positive, this is +1, it implies that the first exponent is greater than the second. So what we do, we choose the greater exponent. That is, we say that the result will have this exponent 3. Fine, done. So if 3 we have chosen, then we need to change this y, and this should also become 3 here. So how will this become 3? Very easy. If we want to convert this number to 10 raised power 3, this will become 0.0820 into 10 raised power 3. So y, to convert it the exponent to 3, we obviously will change it here. We will put an extra 0 here. It will become this thing. So now when we have done this thing, this is called alignment of mantisas. So here and here you can see this mantissa has been aligned. Why do we do this alignment? To get the exponents in same category. Fine, this is 3, this is also now 3. So once this alignment of mantissas is done, now we can easily add or subtract it. What we have to do, the answer will have the same exponent, and this will be subtracted or added, whatever we need. So if we have to perform an addition, for example, so we will directly add this and this. Fine. When we add these two, we get this. So answer is this. But we always normalize things, so we should normalize this, and when we normalize it, it will become this one will come here, this will become 0.1, 0.1, and this will become 10 raised power 4, obviously. So finally we get this answer. This will be the exponent 4, and mantissa will be this thing. So this is the this way we can do addition and subtraction of floating point numbers. Now if we do the same thing in terms of segments, in terms of a pipe. What type of operations will be there? The first will be that we have to compare the exponents. So the first segment of the pipe will be compare the exponents. How do we compare the exponents? By subtraction. Okay, so first job is done. Then the next job will be based on the result of this subtraction, we will do the alignment of mantissas. So the second segment will be alignment of mantissas, right? And when we align these mantissas, that is, we shift it one place. At the same time, we have chosen this 3 as the final exponent. So at the same time, in this segment 2, we will choose the final exponent. Okay. Then in the third segment, we will do the actual operation, that is addition or subtraction. Okay. The third segment is addition or subtraction of mantissas, obviously. Done. And in the last segment, what after addition, if we get this type of number, we have to normalize it. So to normalize this thing, we will do a normalization operation. Fine. So the fourth segment will be normalization of the result. And when we normalize the result, exponent will also get affected. So we need to update the exponent also. So in the segment 4, with normalization, there will be an adjustment in the exponent also. So in this example, it changed from 3 to 4. Right? So this will be the pipe. So we can distinguish between 4 segments here. So how will this become now a pipelining concept? That if we have two numbers, they will be compared by subtraction, then their alignment of mantissas will happen. At the same time, new two numbers will come, their mantissas, their exponents will be subtracted at the same time. Fine. So in the next clock cycle, in the first clock cycle, maybe x1 and y1 will be here. In the second clock cycle, x2 and y2 will be here, and x1 and y1 will be here. Fine. In the third clock cycle, x1 y1 here, x2 y2 here, x3 y3 here. And in the fourth clock cycle, x1 y1 will be here, x2 y2 here, x3 y3 here, and x4 y4 here. So then we can see at the same time 4 numbers are being operated in this pipe. So this is clearly a pipelining concept, and this can only be achieved when we segregate these in terms of segments and put registers in between each segment so as to do the operation. Right? So this is a very simple example of how an arithmetic pipeline exists and it can work. There is another type of pipeline, a pipe, which we use for instructions. We don't use the pipeline processing only for data stream, we also use it for instruction stream. We know a computer, a processor processes data, it performs addition, subtraction, multiplication, fine. But it also does another job, that is execution of instructions. That is, it will take read instructions from the main memory one by one, and then those instructions will be executed by the processor. This is another job done by the processor, that is execution of instructions. Fine. So when a processor executes an instruction, there are it follows a cycle. So it takes one instruction, performs certain steps, then takes another instruction, performs the same steps. So this is called the instruction cycle. In instruction cycle, there occur many steps are there, many phases are there in the instruction cycle. We generally classify them into 6 phases, 6 steps. So first of all, the processor will fetch an instruction from memory. Fine. Since it has to execute an instruction, first of all, it will fetch the instruction from the memory. So from the memory, it will take an instruction, done. Second, it will decode the instruction. Fine. So the instruction is, for example, 11000011. It doesn't know what does it mean. It has to decode it. What is the meaning of this set of bits? This set of bits may mean addition, subtraction, or any other operation. Right? So what is the meaning of the bits which I have just read from main memory? So that is a decoding thing. So it will decode the instruction. The third phase will be that it will calculate the effective address. So if the instruction says it has to do addition, but it will calculate the maybe the instruction is what it reads from the memory, it is referring to some other address in memory. Fine. The instruction itself is pointing to an address in main memory. So this instruction itself is pointing to certain address in main memory. So we have to fetch that, go to that place and fetch that thing. Fine. So this is called calculating the effective address. So once we have done this effective address thing, now we have the effective address of the data. The instruction has to execute on certain thing, but that thing may be that number is not there in the instruction. Sometimes it may be there, sometimes it may not be there. It may be an indirect address. So when it is an indirect address, you have to calculate the effective address. So it will go to that place and make calculations and find the effective address of the data. Once we have found that, then the next step will be fetch the operands from memory. That is, now it knows what it has to do. Now it needs the data on which the operation has to be performed. Right? Decoding told it that it has to do addition. Now on what it has to do the addition, that operands need to be fetched from the memory. Now in the fourth step, it will do the fetching using the effective address. And now it knows what to do. It knows the data on which the operation is to be performed. So now in the fifth step, it will do the operation. That is, it will execute the instruction. It will do the addition, subtraction, whatever it has to do. It will do that in the fifth step. And once operation is done, a result will be produced. and that result it will store at some proper place. So this will be the sixth step in the instruction cycle, storing the answer, right? So this is the general view of the various steps in the execution of an instruction. And we can in a number of cases we can assume that this can be briefed up into four phases only. We can say that it will be like this. This it will be like this. So fetching will be the first phase, and second and third phase will be combined. Decoding and calculate effective address can be combined, and then there will be the fourth phase, that is fetching the operand from memory, and the fifth and sixth can also be combined, right? So for assumption purposes or simplification purposes, we say that this is the first phase. 2 and 3 can be combined and they can be done as a single segment. They can be done simultaneously actually. So we can say we can decode the instruction and calculate the effective address simultaneously. So since we have to create a pipeline, we can say this will be one segment and 2 and 3 will be second segment because they can be done simultaneously. Then 4 will be the segment 3 and 5 and 6 will be segment 4. So if we uh, implement this instruction pipeline using 4 segment theory, then it will be like this. So this diagram shows us an 4 segment CPU pipeline, which is an instruction pipeline. So here we can see we are not doing addition subtraction. We directly we are not doing arithmetic operation. We are just executing an instruction. So we made 4 segments. First segment is fetching the instruction from memory. Second segment is decode the instruction and calculate effective address. Third segment is fetch operand from memory, and the fourth segment is execute instruction. And if you look keenly, this is a very simple diagram. The computer, the CPU will fetch an instruction from memory, done. Then it will decode it, calculate effective address, okay. When it decodes the instruction, maybe the instruction is saying branch. Decoding means it will understand what the instruction is saying. If instead of addition subtraction it is saying branch, branch means it is saying that you jump to another place, fine. So you go to some other instruction, like we say go to in C programming. So if there is a branch, it will not operate normally. Now it has to go some other place. So if there is a branch, obviously program counter will be updated. So if we are on instruction number 4, for example, now branching is saying go to instruction number 100 directly. So PC will not contain 5, it has to be updated to 100. This is simple. And this whole pipe needs to be emptied, because after, if 4 is going on, we cannot take now 5 for fetching, and if we have already taken 5 for fetching, then this will be wrong, because we have to take the instruction number 100 now for fetching because of branch. That means we must clear this pipe. So if there is a branch, we update PC and then empty the pipe, okay. And if there is no branch, normal things are happening. So next step will be obviously fetch operand from memory, done. After fetching the operand, we have already decoded, we have fetched the operand. Now we will do the execution. Execution will be done, and in this segment, at the same time, the answer will be stored somewhere. Let us say the answer is stored in register. So it is happening at the same segment. So execution has completed, done. Now, if there is an interrupt, fine. If there is an interrupt, what will happen? Again, if there is an interrupt, you have to address that interrupt. You cannot say that I will not address this interrupt. I will continue. If I am if I am executing instruction number 7, next I have to execute instruction number 8. But if there is an interrupt, we need to put everything aside. We need to jump onto that interrupt, and the processor needs now to go to that interrupt. So if there is an interrupt handling will again update the PC, and pipe should be emptied. Fine. So it will occur like this. So these two exceptions, branching and interrupt, may change the sequence of the working of pipe. Otherwise, it will be a clear pipelining concept. How? So say for example, the computer starts executing instructions. It takes instruction number 1 here. Fine. So instruction number 1 is fetched in the first clock cycle. Then in the next clock cycle, instruction 1 is in this segment, but instruction 2 at the same time starts to be fetched. In the third clock cycle, one instruction will be here, the second instruction will be here, third will be here. And in the fourth clock cycle, the first instruction will be here in the execution phase, the second instruction will be in this phase, in this segment, the third instruction will be in this segment, and the fourth will be in this segment. And in the fifth cycle, first is complete. Now here it will be instruction number 2, here instruction number 3, here instruction number 4, and here instruction number 5. So this way, this will be a pipelining concept, and in a pipe, things will be done. And at the same time, 4 instructions can be in the pipe. In a non-pipelining system, this is not possible. Only one thing can be done at a time. Processor can take only one instruction at a time. But here in this pipe, at least 4 will be there in the pipe usually. So this whole pipelining thing can also be drawn in a table. Let us draw a table and let us put from here steps or clock cycles. So this is the first, second, third clock cycle or step that is occurring. And from here, let us put instructions, because we have to execute instructions. So this one means instruction number 1, this is instruction number 2, 3, 4, and so on. What will happen in the first step when the computer starts executing instructions? The first step, first instruction will be fetched. In the second clock cycle, the first instruction will be decoded, but at the same time, the second instruction will be fetched. Fine. And in the third clock cycle, the first instruction will be in the third segment, that is fetch operand segment, and second instruction will be in the second segment, DA segment, this thing, and the third instruction will be in the fetching segment. So for we are using here this FI means this segment, fetch instruction segment. DA means second segment, decode instruction and calculate effective address. FO means this segment, fetch operand segment, and EX means fourth segment, execute instruction segment. So this is very clear. First instruction will be executed in this way. So first segment, second, third, and fourth. Second will be like this: first, second, 2, 3, 4, and 5, and it will be like this. We can easily draw this thing. So in the fourth clock cycle, you can see all 4 instructions are there in the pipe. Fourth instruction is being fetched, third is being decoded, second is doing fetch operand, and the first is doing execution. So all are there in the 4 segments. Fine. So this table can be built like this. Now let us take this exception also. Let us say that in the third instruction, it is a branching instruction. So the third instruction is a branch instruction. But when will the processor know that it is branch? Only when it does the decoding. So when the third instruction is decoded, DA here. So when the third instruction is decoded, the processor will know that it is a branch thing. So whenever there is branch, you can see from this diagram, we have to update PC and empty the pipe. So that is what here we can see in the diagram. So after DA, here we are emptying the pipe. When DA occurs for the third instruction, this DA tells us that there is a branch. So you should not now take other instructions, read. You have already read fourth instruction, but that is of no use because we have to branch to some other place, maybe 100th instruction. So this is useless. So this should not continue. After fetching instruction number 4, you should clear the pipe. So no need to decode or do other operations on this instruction 4 because we have to go to some other place. So here we can see this is cleared, pipe is cleared, and once the pipe is cleared, then we can go to the new place, the branching place, for example instruction number 100. So now we will start fetching that new instruction, the branch instruction, and it will continue likewise what we were doing. So first we'll be fetching, then in the next it will be the next instruction will be fetched and the previous will be decoded, and so on. So this pattern will be very similar to like this here: FIDA FOEX, FIDA FOEX. These four will be repeated, fine, and we will continue. So say for example we have 7 instructions, so we will start here. When the 7th instruction will be executed, we will stop here in this table, fine. So we can easily build this table on the concept of this 4 segment instruction pipeline, and we can see in 13 steps these 7 instructions were executed. Had there been no branch, if there had been no branch, so this we would not have emptied anything here, fine. If there would have been no branch, it would have been FIDA FOEX here, then the next would have been here, next would have been here, and the next would have been completed from here. So if you do it on your own notebook, you assume that there was no branch and make the same table, then you will find that at 10 it will end on 10. So 7 here will be EX for 7 instruction. So because of this one branch, pipeline lost 3 clock cycles. And that is what this diagram is also telling us, that whenever there is a branch or an interrupt, pipe needs to be emptied. Because of emptying of the pipe, there obviously will be a loss of clock cycles. So in this example, clearly we are going to 13 clock cycles instead of 10 because of a single branch there at step 3, instruction 3. So branching and interrupt may decrease the efficiency of pipeline, but in general, instruction pipeline is much faster and efficient than a non-pipeline system for executing of instructions. Thank you.